discharge 0 and you operate the pump, that is you close the pump, in this case you see that the head will be maximum. You can see here the head is maximum. So this is known as shut off head. This is known as shut off head. That is corresponding to 0 discharge. But when we open the valve on the discharge side, the head decreases. Here you can see the head decreases. We just discussed this before the break, the head discharge curve. So then in this case, what is happening is that we have this head discharge curve. From where these curves will come, we can run test on the pumps. So when we have this curve here, next the second one, the curve that we can draw, so that can be for efficiency of a pump. So efficiency we denote by eta. This is with respect to discharge. So we will find out that with 0 discharge, 0 efficiency, and it will increase and then it decreases like this. Clear? The third curve that we can draw, that is the brake horsepower. This is the brake horsepower. What is the brake horsepower? bhp. And this is the power input. When we use the term brake power here, clear? The brake power that we can use here, so it means that it is the input power. So this is the input power that is required to drive the shaft. So in this case, you see that when you operate the pump, it will behave like this. Clear? So this is bhp, the brake horsepower, and this is the discharge. When we combine these three curves, so this is what we get. And these curves that we obtain, this will be at a constant speed. We will operate the pump at a constant speed, so we can draw these curves. Clear? So what is the advantage that we can get? Basically, these are the performance characteristics. These are the performance characteristics for a centrifugal pump. So now in this case, you can see that this is the maximum efficiency. We can evaluate the performance of a pump. This is the maximum efficiency. So this is eta maximum. This is eta maximum. Now for maximum efficiency, because what is required is that we want to operate the pump corresponding to the maximum efficiency. This is what we want, that the machine that works, that should be efficient. So this is your eta maximum. This is the maximum efficiency here. So in this case, you see that if I come here, this will be the head that will be corresponding to the maximum efficiency. This is the head that is corresponding to maximum efficiency here. This is the head that is corresponding to the maximum efficiency. And this will be the design flow rate. This is the discharge that the pump should provide, because under this condition, the pump has maximum efficiency, and this is what we want. And for this maximum efficiency and this head and the design discharge, this will be the power required to drive the pump. This will be the input power required. So you can see that we can evaluate the performance of pumps from these curves. But these curves, they are drawn for a constant speed. If you change the speed, then there will be, the shapes will be similar, but there will be a shift in the curves. Clear? These are the curves for a centrifugal pump. That is our main focus. Now in this case, these are the same curves, but these are for the mixed flow centrifugal pump. It means that the flow is partly radial and partly axial. So you can see here that for maximum efficiency here, this is maximum efficiency. So this is what we call it as the BEP, best efficiency point. This is the best efficiency point here. Now for this will be the design flow rate, because under this condition, for this flow rate and this head, we have maximum efficiency of the pump, and this will be the input power required, and you can see the water power, that is the output. So the output power, this is here, this is the output power. So this is how we can evaluate the performance of pumps. Clear? At a constant speed. For example, for this data which is provided here, this diagram is from the textbook. So we have the mixed flow centrifugal pump that is operated at 1450 RPM. This is operated at 1450 RPM. Whenever you see this small e, it means that it is corresponding to the best efficiency point. So NE is the rotative speed corresponding to the best efficiency point, means the maximum efficiency. Clear? Similarly, this is a diagram for axial flow pump. These are the characteristic curves for axial flow pump. So you see here for maximum efficiency, this is the optimum point of operation. The pump that will operate at this point here, that will be corresponding to the maximum efficiency. Clear? And this will be the input power required to drive the pump. And this diagram is for axial flow pump that is corresponding to the 450 revolutions per minute. Clear? For this speed, these curves are drawn. So these are given in our textbook. This is how we can evaluate the performance of pumps. Now, how to determine this operating point of a pump? You see the optimum point of operation. So how we can determine this operating point of a pump so that the pump can operate at this point, and that should be corresponding to the maximum efficiency. That should be corresponding to the maximum efficiency. So for that, what we have is known as the graphical method for finding the operating point of a pump and pipeline. First, what we do is that we have this head discharge curve. So this blue line, it represents the head discharge curve. And from where this curve will come, it will come by running tests on the pump. Just like we have fluid mechanics 2 lab, you conduct different experiments. So we can have a head discharge relationship for a centrifugal pump. This can be an experiment. So running that experiment, you will be able to draw this curve, which is the pump characteristic. Clear? That gives us the head discharge relationship. Clear? So the mode of operation of a pump depends on the system in which it is operating. So we have the pump characteristic curve, and we already know that it shows the relationship between the head developed by the pump and its rate of discharge when the pump is running at a given speed. So this is known as the pump characteristic curve. It shows the characteristics of that specific pump. Clear? Second, we have to see that what is the requirement of the system or the pipeline. What is the requirement of the system or pipeline? So you will get this curve here, which is shown in purple color. You can get this curve. How to get this curve? You see that we need that the pump should provide a static lift. This is what the pump is required to provide the lift. Clear? We earlier talked about this. In this diagram here, we earlier talked about this, that the pump should provide a lift, this delta Z. But then there are losses associated. So the pump should provide a lift more than this delta Z to account for the losses. Clear? This is delta Z. So this is the required by the system. You see, this is the system. We want to take the water from one reservoir to another reservoir, and the pump has to provide this lift. So this is what is required by the system, and the pump will provide this lift, accounting for the losses. Clear? So how to calculate that, what is the requirement of the system? You already solved problem on this even in your midterm exam also. You can write the energy equation between point here and between point here for this system, and considering this lift here, so then we can apply the energy equation and we can calculate that what is the head required by the pump. So this is the required by the system actually. Clear? From there we can consider this HP, and that will be required by the system. And one is the head that should be supplied by the system, that coming from this head discharge curve for the pump. This is coming from here. This is for the pump. This is the curve that we develop for a pump. That if this is the head, this is the discharge. If this is the discharge, this is the head, and so on. And one is the system characteristic. What is this pipeline or system characteristic? This is the requirement of the system in which the pump is operating. Just like I show you the diagram. So the system requires a static head. This is the delta Z that the pump need to provide. But as the discharge increases, this becomes a curve. Why it becomes a curve? Because we already discussed that HF, this is proportional to V square. We already discussed. Clear? So it means that this HF, it is proportional to Q square. Approximately, we can write down that it is proportional to Q square. So that's why this head loss, it is proportional to, approximately proportional to Q square. So as the discharge increases, you can see the losses increases. You can see the losses increases as the discharge increases, the losses increases. Clear? So that's why we have this curve. If there are no losses, then it should be this static lift that the pump need to provide. So that's why we get this curve. So this is the system requirement, including the static lift and the head losses. So how to determine the operating point of a pump? How to determine the operating point of a pump? We have this pump characteristic which will come by running test on the pump, and this curve will come from the system requirement in which the pump is operating. So this we call it as the system characteristic curve, pipeline or system characteristic curve. It shows the relation between the required pumping head and the flow rate in the pipeline. It shows the relation between the required pumping head and the flow rate in the pipeline. So the point where the two intersect, that will be the operating point of the pump, because at this point, this is the head required by the system, and from the pump characteristic, this is the head supplied by the pump. So this is the operating point, what is required by the system, that is supplied by the pump. This is the operating point of a pump. The pump should operate at this point. So this is the graphical method for finding the operating point of a pump and pipeline. Now, the actual pump operating head and flow rate are determined by the intersection of the two curves. The actual pump operating head and flow rate are determined by the intersection of the two curves. This is what I said. So we have this operating point of a pump that is determined from here. So this shows that what the system requires, the pump is providing that job. So that pump is then suitable. And remember that this operating point, this must be corresponding to the maximum efficiency. This must be corresponding to the maximum efficiency. As you see here, it must be corresponding to the maximum efficiency. This point that we determine, that must be corresponding to maximum efficiency. If it is not, then it means that the pump is not suitable for that job. So this point that we determine from here, this operating point must be corresponding to maximum efficiency. It must be corresponding to maximum efficiency. If not, then it means this pump is not suitable for this job. Again, because the pump is not operating for the maximum efficiency, we want the pump to operate for maximum efficiency. Clear? Now, if the pump is, let's say here, if the point is here, if we consider a point other than this point, intersection point, then the pump will not be suitable. How? For example, you consider here. So for this point, this discharge, this is the head that is required by the system. That is required by the system. But for this discharge, the pump is providing this much head. The pump is providing this much head. So it means you require 10 feet of head, but the pump is providing 12 feet of head. So it is useless. Additional head is provided. No need. Similarly, if the point is here, so it means that what this means, if the point is there, if the point is here, then it means the system requires this much head. This is required by the system. But where is the pump characteristic? The pump characteristic is here. So it means that the pump is supplying only this much head. So it means the required lift is not possible. The system requires, let's say, 15 feet of lift. This is the system required, but the pump is here. The pump can only provide 10 feet. So then this pump is not suitable for that specific job. So this is how graphically we can determine the operating point of a pump. Next, we study very important specific speed of pump. Now, specific speed is a number. This is a number you can see here. Specific speed is a number. So this number helps us to select a suitable pump. For this purpose, this concept is used. So specific speed is a number that defines the type of pump, whether it is radial flow, mixed flow, or axial flow. Clear? So this NS here, this is given by this equation, and this specific speed that must be corresponding to the best efficiency point. Remember, when we want to operate the pump should operate at maximum efficiency for any given specific job. So in this case, this equation will give us the specific speed for the given conditions, and then that specific speed we can use here, and we can determine that the suitable pump that should be radial flow, mixed flow, or axial flow pump. So in this case, in this equation, this NS, this is from our textbook, all the notations. So NS is the specific speed. NE This is the rotative speed of the impeller in revolutions per minute. Whenever you see the term E, this subscript E, it means that it is the speed corresponding to the best efficient point, best efficiency point, corresponding to the maximum efficiency. We have the discharge, so it is in gallons per minute, and H is height, are those that occur at the point of optimum operating efficiency, commonly referred to as the best efficiency point. For larger pumps, we will solve a problem on this, how to calculate this specific speed, and then come here and see that what type of pump is represented for that given conditions. Clear? For large pumps, specific speed has sometimes been calculated using Q expressed in CFS rather than gallons per minute, in which case this is the relationship. So we can convert the specific speed from gallons per minute to CFS, cubic foot per second. Clear? In System International, in SI units, specific speed of pump is defined by this equation. This is also given in your textbook. So in this case, this omega, that is corresponding to rotative speed corresponding to the maximum efficiency. It is in radians per second. Q is the discharge and H is the meter. So these are those that occur at the point of optimum operating efficiency, commonly known as best efficiency point. So you can calculate this specific speed in SI, and then we can use the same graph. This is for SI at the top. This is for the specific speed in SI system, and still you can determine what type of pump is this and the corresponding efficiency. And we can also use in the system where NE is represented by revolutions per minute, discharge in gallon per minute, and H is in feet. And also the relationship between the System International specific speed and the traditional mode of expressing the specific speed is this. Also we can convert the specific speed that is calculated for gallons per minute discharge into SI system using this relationship. Clear? So the whole conclusion from this topic is that specific speed, it is a number that we can calculate for any given situation. The rotative speed of impeller we know, the discharge we know, the head required we know. So we can calculate this specific speed, and then we can enter to this graph and we can determine what type of pump is this. Clear? So it can tell you that it is a radial flow, or it is a mixed flow, or it is axial flow pump. And then you can determine even the efficiency. For example, for 2000 NS, so what is the type of pump? Radial flow. And what will be the efficiency that can be provided by the radial flow? It will be this much. So this is important parameter that we use for pumps as well as turbines. Clear? So it helps us to select a suitable turbine. We know from this what type of turbine is this. We will solve a problem. It will be further clear from that. Now these ranges are given here. We have radial flow impellers for between 500 and 5000. Then we can say that the pump is radial flow pump, radial flow impeller. If the specific speed is between 4000 and 10,000, then in that case we have mixed flow. And if it is between 9,000 and 15,000, then we say that it is axial flow. Clear? So 9,000 and 15,000 here. So we say that it is axial flow. For the SI system of units, so if the specific speed is between 0.2 to 2, we will say that the type of pump is radial flow. And if it is in this range 1.5 to 3.7, we say it is a mixed flow. And if it is 3.3 to 5.5, we say it is axial flow pump. Next, we have peripheral velocity factor. So in this case, this peripheral velocity factor, it is the ratio of the peripheral velocity to under root 2gh is referred to as the peripheral velocity factor. It is denoted by phi. So thus for a pump, this phi, this is known as U2. This is the velocity. You see, we have a pump vane or turbine. So you can see here the water enters into this vane here. This vane is moving. So at the inlet, you have U1. This is what we discussed in the previous chapter. And then it exits here. And this also moves at the exit. We have the inlet exit velocity diagram. So this will be U2. So this is how it is written here, that U2 divided by under root 2gh. This is U2 divided by under root 2gh. And then from here, U2 is equal to phi into under root 2gh. Now this U2 is the peripheral speed. This U2, this is the peripheral speed of the impeller. For axial flow pump, it is the vane tip speed. For axial flow pump, it will be the vane tip speed. Because just like you see in a case of a vane, as you see the blades of the vane here, so at this tip here it will be represented this U2 at the vane tip. Clear? So this is the velocity that we have to consider. Now what is the use of this peripheral velocity factor? Why we define it that it is the ratio of peripheral velocity to under root 2gh. This is the peripheral velocity factor denoted by phi. So from here we can say that U2 is equal to phi into under root 2gh. What is the use of this? So for any pump, its peripheral velocity range from 0 up to some maximum. Clear? Under a given head. So now you can see that for a given head, you see this can be, it can have some range from 0 to some maximum value. So it means that correspondingly phi will vary through a wide range. But we are interested in the peripheral speed that is corresponding to the maximum efficiency. We are interested that is corresponding to the maximum efficiency. So in that case, we denote phi by phi e. So it means that this is peripheral speed factor, this is peripheral velocity factor that is corresponding to the maximum efficiency. And then from here, what we can write down? We can write down U2 is equal to 2 pi r NE by 60 NE. This is in revolutions per minute. So this is the relationship between this is the tangential velocity. So it is in the linear direction as we discussed in the previous chapter, momentum and forces in fluid flow. So this U, this is equal to R into omega. This is equal to R into omega. This is the relationship between the rotative speed, angular speed and linear speed. So omega is equal to 2 pi n by 60 as we discussed when we discussed the efficiency of the pump. So 2 pi r NE by 60. Clear? This omega, this is equal to 2 pi in radians per second. So this is 2 pi n divided by 60. So this is what is written here. Now this NE, this U2 is equal to phi e into under root 2gh. And from here, we can get the diameter of the impeller of the pump. Similarly, in the BG units, so this is the diameter that can be written in terms of head, rotative speed, and peripheral velocity factor corresponding to the maximum efficiency. So these equations are then used to estimate the diameter of the impeller of the pump if the specific speed of the pump is known. So you see, we are using this in the preliminary design of the pump. We can estimate the diameter of the pump if we use this peripheral velocity factor. And from where this will come? This will come here. You can see this is phi e. This is the phi e curve, peripheral velocity factor curve. For any given specific speed, let's say 5,000. So then 5,000, and this is the value of phi e, 1.5. This is the peripheral velocity factor corresponding to the maximum efficiency. Clear? This is corresponding to the maximum efficiency. And then this you can use here to estimate the diameter of the impeller. So this is the use of this concept here, why we study peripheral velocity factor. Now, next is pumps operating in series and in parallel. Pumps operating in series and in parallel. So for two pumps that are operating in series, head will be 2 times. And for two pumps operating in parallel flow rates, discharge will be 2 times. So first we consider pumps in series. So in this case, you can see that when two pumps, when this is pump number 1, this is pump number 2, when they are operated in series, the head is twice. The head is 2 times. So two identical pumps, centrifugal pumps operating at the same speed with the same discharge contribute the same pump head. So we have H1, and then H1 is equal to H2 for two identical pumps. Clear? Since the inlet to the second pump is the outlet of the first pump, the head produced by both pumps is the sum of the individual heads. The discharge from the inlet of the first pump to the outlet of the second pump remains the same. So when two pumps are connected, can be more than two, but just for understanding purpose, when two pumps are connected in series, so the head will be 2 times because they are identical. Clear? And normally we do this because if a smaller pump is connected to a larger pump, or a larger pump is connected to a smaller pump, then there will be operational problems. So that's why it is better that when we connect the pumps in series or in parallel, then they should be identical. Clear? So that the load is equally distributed for efficient working. When we have pumps in parallel, then in that case the head will remain the same, and then the discharge will be 2 times. Then the discharge will be 2 times. Clear? Because you see here, this is providing a discharge, this is providing a discharge, so it will add up. So the discharge will be 2 times for two pumps in parallel. So two identical centrifugal pumps operating at the same speed with the same head contribute the same pump discharge. The discharge produced by both pumps is the sum of the individual discharges. Clear? So this is the case when two pumps are connected in series, the head is 2 times, and when they are connected in parallel, the discharge is 2 times. But because they are operating in a system, so as the system curve remains the same, then in that case, this will not be the case. For example, what I say is that when two pumps are connected in series, and we have the system curve that we just discussed, we have the system curve. So then in that case, you see this is a single pump. This is one pump operating here. This is a single pump. And these are two pumps that are operating. So now in this case, this is the head required by the system. and this is the head that should be supplied by the two pumps that are operating in series. So now in this case you can see that the head is not necessarily doubled. Clear? So for two identical pumps in series, both the actual head gained by the fluid and the flow rate are increased, but neither will be doubled if the system curve remain the same. So if the system curve is the same, you see the head that is produced by the two pumps will not be doubled, because it should provide the head that is required by the system. So that's why in the system, it does not mean necessarily that the pump should provide the double head if they are connected in series. So the operating point is at A for one pump, but then moves to B for two pumps in series. And same is the case for pumps operating in parallel. You can see here in parallel the discharge was double. But now because the system characteristic curve, it remains the same. When we have a one pump, this is the discharge which is provided. This is the discharge which is provided. And for the two pumps, then this is the discharge. So this is not necessarily doubled. You see here, this is not necessarily doubled. Depends on how the system requires the two pumps should operate. So for two identical pumps in parallel, the combined performance curve is obtained by adding flow rates at the same head as illustrated. The flow rate for the system will not be doubled, clear, with the addition of two pumps in parallel if the same system curve applies. However, for a relatively flat curve, system curve, a significant increase in flow rate can be obtained as the operating point moves from point A to point B. So if you see the curve is here, then the increase in discharge is small. But if we have a flat curve, then in that case the discharge will be increasing more. Next, we solve one or two problems to learn how we apply the concepts that we just learned for solving the problems. So we have, this is problem from our textbook, chapter 15 of the textbook. The diameter of the discharge pipe of a pump is 6 inch and that of intake pipe is 8 inch. The pressure gauge at discharge reads 30 psi, 30 pounds per square inch, and the vacuum gauge means negative vacuum gauge at intake reads 10 inch of mercury. If the discharge of water is 3 CFS cubic foot per second and the brake power is 35, this is the input power, brake power. Find the efficiency of the pump. Now we need to calculate the efficiency. The input power is given, we need to calculate the output power. Then we will be able to calculate the efficiency of the pump. The intake and discharge are at the same elevation. The intake and discharge are at the same elevation. So how we do it? Since discharge is given 3 CFS, we can calculate, this is the discharge side. So we denote by small d, this is the discharge side, suction side, sorry. This is the suction side S, and this is the discharge side. So now the diameters are given, we can calculate the velocities on both sides, clear? This is the suction side and this is the discharge side. So we can calculate the velocity on the discharge side and we can calculate the velocity on the suction side using the continuity equation or discharge by the cross-sectional area. Now we can calculate the head that is developed by the pump. So as I said before, how to calculate that? Simply the difference of energy on the two sides. So before we do that, you see here simply difference of the energy on the two sides. On the discharge side minus the total energy on the suction side, that will be the head developed by the pump. We do not write down Z here because it is given that the intake and the discharge are at the same elevation. So Z1 is equal to Z2. It means that Z1 that is equal to Z2. Now, since pump is the liquid which is used, and pump is adding the energy to the liquid, that is water. So that's why we need to convert this pressure head which is given in terms of mercury into water. So you can use this relationship here. Clear that 29.9 inches of mercury is equal to 33.9 inches of water. So you can see in terms of units here. Clear? So for 10 inch, what should be the feet of water? 29.9 inches of mercury will be equal to 33.9 feet. Clear? So in 10 inches, how many feet of water we have? And why we use the negative sign? Because the negative sign, we have vacuum gauge. We have vacuum gauge. It is given that we have vacuum gauge. So that's why we have the negative sign. Clear? So 29.9 inches of mercury, that is equal to 33.9 feet of water. So in 10 inches of mercury, how much feet of water will be there? 11.34. Negative vacuum gauge, so negative pressure. Clear? So that's why we write down here. The rest you plug in the values, you can calculate. This is the head developed by the pump. And now the efficiency we can calculate the output power divided by the input power. So the output power is gamma QH divided by 550, so that it is in horsepower. Because this is given 35, the input power. So this is in horsepower. Clear? HP. So this is divided by 550. So now the efficiency comes out to be 0.81, or this is equal to 81%. Next we have problem 15.14. We have a centrifugal pump that is installed to deliver water from a reservoir of surface elevation 0 to another reservoir of elevation 300 feet. So now delta Z is given, that is 300 feet. This is delta Z, this is given 300 feet. The 12-inch diameter suction pipe, for which the friction factor is given, that is 0.020, that is 100 feet long, and the 10-inch diameter discharge pipe, for which F is given, F is equal to 0.026, is 5,000 feet long. The pump characteristic at 1200 RPM is defined by, this is the pump characteristic which is given. The head discharge relationship, the pump characteristic, and this we can develop by running test on the pump, where HP is the pump head and Q is the discharge. Compute the rate at which this pump will deliver water under these conditions. So now the pump characteristic is given. Clear? You see here that we already discussed, we have this discharge and this is head. So now the pump characteristic is given. This is given by this equation here. Now we want to calculate the discharge that the pump should provide. So what we will do is that we will develop a system head characteristic curve. We will develop a system characteristic curve, and where to intersect, that will be the required discharge. Clear? So for that, what we do is that for the system, we develop the system characteristic curve. For that, we will apply the energy equation between one point here. You select one point here, and then you select another point here, and you apply the energy equation considering the losses. We will neglect the minor losses, only consider the major losses. So what we will have, you will write down the equation. So that will be equal to P1 by gamma plus that will be equal to V1 square by 2G plus Z1 plus we have the major losses in this pipe here, so it will be equal to HF1, the major head loss in the first pipe. This will be plus, because we have pump, it will add the energy, so we have plus we have HP, and then at this point 2 it will be equal to P2 by gamma. This will be equal to P2 by gamma plus V2 square by 2G plus Z2 plus HF2 this is the head losses due to friction in this pipe here. So now in this equation you can see at 1 P1 by gamma is 0. At 1 the velocity is very small as compared to the pipe flow, so this is 0. Similarly at point 2 P2 by gamma is 0, and here the velocity is very small, so these are all zeros. Clear? So in here what we say is that Z1 minus Z2, that is your delta Z, which is given 300 feet. So this is given to us, Z1 minus Z2, this is 300 feet, that is given to us. Now when you simplify this equation here, F value is given, the friction factor are given for both the pipes, so you will get this equation. Clear? You will get this equation. This is delta Z, 300 feet, which is given, this one here. So when you simplify V1, because V1 we don't know the discharge that we want to calculate, so this V1 and V2 we can write down in terms of the discharge. The diameter of the pipes are known here, and here the diameters are known. We can write down V1 and this is V2. This is V2. We can write down in terms of the discharge, and that we can put here. When you simplify, we will get this from this equation, then we get this expression. So this is now the system characteristic curve. This is what we obtain, this blue line. Now we obtain equation for that. And for the pump, this is given. This is given here. This is for the pump. So now the left hand side of both equations are equal. For this point here, we can equate the two equations. We can equate the two equations. So equating the 2H, from here only unknown is Q. So Q is equal to 1.526 CFS. This is the required discharge, and this is its value in gallons per minute. So this is how we calculate the discharge of the pump, the rate at which this pump will deliver water under these conditions. Next we have this problem 15.8.4. The question is, find the specific speed of a 10-stage pump that develops a total head of 600 feet at a capacity of 1600 gallons per minute when operating at maximum efficiency at a rotative speed of 900 revolutions per minute. For this given condition, what is the specific speed, and then what type of pump is this? Clear? That we have to calculate. So since in calculation of specific speed, the head that we use in calculation of specific speed, if I go back to that equation of specific speed, so in this equation of specific speed, this H that we use, that is for a single stage pump. This is for a single stage pump. Now in the problem, it is given that we have how many stages of the pump? We have a 10-stage pump. So now we have to convert this into a single stage pump. Clear? So that's why for a single stage pump, the total head developed is 600 feet for 10-stage pump. So then 600 divided by 10 stages, it means that this is 60 feet head developed per stage. This is the equation. All the data is given. You can put and from here the specific speed is 1670. So what type of pump is this? What is the type of pump for this specific speed? So you can see here that's what is the value, 1670. So 1670 is somewhere here. So 1670 you go up. What type of pump is this? Radial flow. That is the suitable pump for this given condition, the radial flow, and this will be the corresponding efficiency here. And even this is the peripheral velocity factor that you can horizontally come here, read the peripheral velocity, and you can estimate the diameter of the impeller also. So the type of pump is radial flow. The type of pump is radial flow.